the sets in a partition, script P, are called pieces or blocks of the partition. Now, there is a very strong relationship between a partition and a equivalence relation. So next is the theorem we will prove. Let tilde be an equivalence relation on a set S. Then the set of all equivalence classes for the elements of S is a partition of the set S. Conversely, let script P be a partition of the set S, and let P be a relation on the set S defined by A is related to B if and only if A is in the same block as B. Then the relation P is an equivalence relation. On the set S. So proof. Let tilde be an equivalence relation on the set S. Notice that the empty set is not in the set of all the equivalence classes for the elements of the set S, since every equivalence class of the element A, which again is all elements in the set S that are related to A, every equivalence class has at least one element, because the equivalence relation is reflexive. So each equivalence class for an element A contains at least the singleton A. Further, even if each equivalence class for an element A in the set S has exactly one, the union of all the equivalence classes in the set of the equivalence classes for the elements of the set S, the union of all those elements is the entire set S. So now suppose that there exists an element X such that X is in the intersection of the the equivalence class of A with the equivalence class of B, where those two sets are not equal, then X is in an element in the equivalence class of the element A, and X is in the equivalence class of the element B. And as X is in the equivalence class for the element A, X is related to A, and so A is related to X, since the relation tilde is symmetric. And as X is in the equivalence class for the element B, X is related to B. And since A is related to X and X is related to B, A is related to B because the relation tilde is transitive. But if A is related to B, then the equivalence class for the element A is exactly the same as the equivalence class for the element B. Every element in A is related to the element of B, and every element in the equivalence class of B is related to the element A. This is a contradiction. Hence, by contradiction, there does not exist an element X such that X is in the intersection of A, or the equivalence class of A with the equivalence class of B when those two sets are not equal. So the intersection of these two equivalence classes is the empty set. They are disjoint. And therefore, the set of all equivalence classes for the elements in a set S is a partition of the set S. So conversely, let script P be a partition of the set S, and let P be a relation on the set S defined by A is related to B if and only if A is in the same block as the element B. Then since A is in the same block as itself, the relation is reflexive. So now suppose that A is related to B, then A is in the same block as the element B, and so B is in the same block as the element A, and hence B is related to A, and so the relation is symmetric. So now suppose that A is related to B and B is related to C. Then A is in the same block as the element B, and B is in the same block as the element C. And so A is in the same block as the element C, and hence A is related to C, and so the relation is transitive, and therefore the relation P is an equivalence relation. On the set S. Okay, so new definition. Let R be an equivalence relation, or be any relation, a relation on a set S, and let X and Y be elements of the set S such that X is not equal to Y, that is, X and Y are distinct elements of the set S. Then the elements X and Y are comparable if either X is related to Y or Y is related to X, and the elements X and Y are incomparable if neither X is related to Y nor Y is related to X. New definition. A relation R on a set S is anti-symmetric if X is related to Y and Y is related to X only when or only if X is equal to Y. So now we will use this new property to define a new type of relation. A relation R on a set S is a partial order or partial ordering on the set S if it is reflexive, anti-symmetric, and transitive. Now, if in addition, every element of S are comparable, so I should say all elements of S are comparable, then the relation is a total order or total ordering on the set S. A set together with a partial ordering is called a partially ordered set or poset for short, and a set together with a total ordering is called a totally ordered set or it is called a chain. So let's look at an example. Let U be the universal set the set U together with the relation is a subset of is a poset. For every set A in the universal set U, A is a subset of itself, and so the relation is a subset of is reflexive. Now suppose that A is a subset of B and B is a subset of A, then A and B are the same set, A and B are equal, and so the relation is a subset of is anti-symmetric. So now suppose that A is a subset of B and B is a subset of C. So let X be an element in the set A. Then Since A is a subset of B, X is an element in the set B. And since B is a subset of C, X is an element in the set C. That is, if X is in the set A, then this implies that X is in the set C, and hence A is a subset of C. And so the relation is a subset of is transitive. And therefore, since the relation is a subset of, is reflexive, antisymmetric, and transitive, the set consisting of the universal set, the universal set together with the relation is a subset of, is a poset. Now suppose that A is not the empty set, B is not the empty set, and A and B are disjoint. Then neither A is a subset of B, nor is B a subset of A. And so the relation is a subset of is not a partial order, rather a total ordering. Since not every pair of elements are comparable.